Welcome! In this session, we'll explore a fascinating computational geometry problem titled Maximum Number of Darts Inside of a Circular Dartboard. We'll break down the problem, examine potential approaches, and ultimately identify an efficient solution. Let's get started. The problem involves determining how many darts can fit inside or exactly on the boundary of a circular dartboard. Each dart is represented by a coordinate on a 2D plane, given in the points array. The dartboard has a radius r, and its center can be any point on the plane. To decide if a dart is within the dartboard, we check if the Euclidean distance between the dart and the center of the dartboard is less than or equal to r. Our goal is to find the maximum number of darts that can satisfy this condition for any possible placement of the dartboard. The output of the problem is a single integer representing the maximum number of darts that can fit inside or on the boundary of the dartboard. Let's look at a few examples to clarify. In the first example, the given points are 2, 0, 2, 0, 0, 2, and 0, minus 2, with a radius r equals 2. If we place the dartboard at the origin 0, 0, all 4 darts lie exactly on its boundary. Thus, the result is 4 since all 4 darts are included. In the second example, the points are 3, 0, 3, 0, 0, 3, and 0, minus 3, again with a radius r equals 2. Here, no matter where we position the dartboard, none of the darts fall within or on the boundary of the dartboard. Their distances from any potential center exceed the radius. Therefore, the result is 0, as no darts fit in this case. Moving on to the third example, the points are 1, 2, 3, 5, 1, minus 1, 2, 3, and 4, 1, with r equals 2. In this example, we can achieve a maximum of 2 darts within the dartboard by carefully choosing its center. For instance, centering the dartboard at 1.5, 2.5, would include darts 1, 2, and 2, 3. Alternatively, centering at 3, 4, could also include 2 darts. Regardless of the placement, the highest number of darts that can fit is 2. This demonstrates how the dartboard's position greatly influences the outcome, and efficient computation is key to solving this problem. To summarize, the key constraints include up to 100 dart positions and a radius between 1 and 5,000. The dartboard can be placed anywhere, and darts on the boundary count is valid. It's also crucial to handle precision errors carefully, especially when calculating distances. Finally, edge cases include scenarios like all darts inside the dartboard, none fitting, or minimal input sizes. For example, a single dart at 0, 0, with r equals 1 would output 1, while widely separated darts with a small radius would yield 0. Understanding these nuances is essential for implementing an accurate and efficient solution. To start, let's consider the brute force approach, which is the most intuitive way to tackle this problem. The idea is based on the fact that a unique circle can be defined by any 2 points and a fixed radius. Using this, we can iterate through all possible pairs of darts to identify potential circle centers. For each of these circles, we then determine how many darts lie within the circle by checking every other dart. While this approach is straightforward, it involves a nested loop structure, one for selecting pairs of darts to define potential circles and another for counting the darts inside each circle. This results in a time complexity of n cubed, where n is the total number of darts. While the space complexity is minimal at 1, the cubic time complexity makes this approach impractical for large inputs, especially when n is in the range of 10 to the power of 4. The computational cost grows rapidly, making this solution infeasible for larger datasets. Now, the optimized approach leverages geometric properties to improve efficiency. Instead of iterating through all pairs of darts, we treat each dart as a potential center for the circular dartboard. Using geometry, we calculate all possible circle centers for a given radius, which can be defined either by 1 point or 2 points. A key observation here is that if a circle is defined by 2 points, the center lies on the perpendicular bisector of the line segment connecting those points. Additionally, the distance between these 2 points must be at most 2 or to define a valid circle. By calculating potential circle centers using the midpoint formula and the given radius, we can then count how many darts fall within each circle using efficient geometric checks. This process involves iterating through all pairs of darts, calculating potential circle centers, and counting the darts within each circle, while maintaining the maximum count of darts inside any circle. This approach avoids unnecessary redundancy and focuses only on valid circle configurations. When we analyze the complexity of this optimized approach, the improvements become clear. The time complexity is reduced to O(n)(, as we only iterate through all pairs of darts and perform constant time calculations for each pair. The space complexity remains O(1), as no additional data structures are needed beyond the variables for calculations. Although this approach is not linear, it is a significant improvement over the O(n)³ brute force method. However, it's worth noting that while quadratic time is acceptable for the given constraints, this approach still has its limitations when scaling to extremely large inputs. Additionally, while a grid-based alternative could be considered, discretizing the plane into a grid creates its own challenges. This method would require high memory usage and could suffer from precision issues due to floating-point arithmetic, making it impractical for our purposes. Ultimately, the chosen strategy is the optimized O(n)² approach. This method strikes the right balance between simplicity and efficiency. By avoiding the cubic complexity of the brute force method and leveraging geometric insights, this approach minimizes redundant calculations and ensures accurate results. It is robust enough to handle edge cases such as overlapping darts or darts lying exactly on the circle's boundary, thanks to precise mathematical checks. While it is not the fastest possible algorithm, its quadratic complexity is well suited to the problem's constraints and avoids the numerical instability associated with grid-based methods. The elegance of this solution lies in its ability to calculate all potential circle centers efficiently and count the darts within those circles in a straightforward manner. This makes it both practical and scalable for the given input sizes. In this problem, we are tasked with identifying the maximum number of darts that can fit inside a circle of radius R on a 2D plane. Each dart is represented as a point with x and y coordinates. To solve this, we need to understand the properties of circles. A circle is defined by its center, denoted as cx, psi, and its radius r. To determine whether a dart lies inside the circle, we calculate its Euclidean distance from the center using the formula, the square root of x cx squared plus y psi squared. If this distance is less than or equal to r, the dart is inside or on the circle's boundary. A key observation here is that a circle enclosing the maximum number of points will either pass through at least 2 points or be tangent to a single point if no other points fit within its radius. This means the solution revolves around identifying potential circles that pass through pairs of points on the plane. To implement this, we start with a brute force approach. First, we iterate over all pairs of points, aiming to calculate the potential centers of a circle with radius r that passes through both points. For each pair of points, P1 and P2, two candidate centers can be derived because the perpendicular bisector of the line segment connecting P1 and P2 intersects the circle at 2 points. Let the coordinates of P1 and P2 be x1, y1, and x2, y2. The midpoint of the line segment is calculated as the average of their respective coordinates. Next, we compute the distance, d, between the 2 points. If this distance exceeds 2r, no valid circle exists because both points cannot fit within the circle. However, if d is less than or equal to 2r, we calculate the offset for the perpendicular directions. This offset is determined by taking the square root of r squared minus half of d squared. Using this offset, we derive the two candidate circle centers by adding and subtracting scaled components of the perpendicular slope to the midpoint coordinates. Here, the perpendicular slope components are calculated using dx and dy, which represent the differences in x and y coordinates between P2 and P1. Once we have the two candidate circle centers, we proceed to count how many darts lie within each circle of radius r. This involves iterating through all the points, checking whether their distance to the candidate center is less than or equal to r. After counting the points for both candidate circles, we update the maximum count of enclosed darts if a higher count is found. To ensure correctness, we also handle edge cases. For example, if there's only one dart, the maximum is trivially 1. When all darts are collinear, each pair of points is still considered, so the algorithm remains valid. Additionally, for large values of r, where all points may fit within a single circle, the algorithm accounts for this efficiently. The geometric principles of circle construction, such as using the perpendicular bisector and midpoint, ensure precision in calculating potential centers, while considering 2 centers per pair maximizes our search space. Efficiency is an important consideration since the brute force approach involves iterating over all pairs of points, resulting in n squared complexity for calculating circle centers. Counting points within each circle adds another n, leading to an overall time complexity of n cubed. To improve efficiency, we can use spatial data structures like KD trees or quad trees to optimize the point-in-circle checks. These structures allow for faster range queries, significantly reducing the time needed to count points within a circle. Additionally, redundant calculations can be avoided by memoizing results for pairs of points that have already been processed. In terms of data structures, we use a list of points to store the dart positions as tuples of x and y coordinates. We also use counters to track the number of darts within each candidate circle. If optimized further, spatial data structures can become an optional but powerful addition for handling larger input sizes efficiently. Finally, let's analyze the complexity of the algorithm. The time complexity is dominated by the pair iteration, which is n squared, and the point-in-circle check for each candidate center, which is n. Combining these, the overall complexity is n cubed. Space complexity, on the other hand, is relatively modest at n, as we primarily store the list of points and use a constant amount of additional space for intermediate calculations. Optimizations using spatial data structures like KD trees or quad trees could improve point-in-circle checks but would require additional space for the tree structure. This balance between time and space complexity makes the algorithm efficient enough for moderate input sizes, while the potential for optimization ensures scalability for larger datasets. With this understanding, we've now covered the core concepts, implementation steps, and performance analysis for solving this problem effectively. Here, we start by importing the necessary mathematical functions and defining the solution class. The main function, numberPoints, takes 2 inputs, a list of points representing dart positions and the radius of the dartboard. To calculate the distance between 2 points, we define the helper function distance. It uses the Euclidean distance formula to measure how far apart 2 points are in a 2D plane. Now, since the task involves finding circles that can enclose the maximum number of darts, we define another helper function, find_circle_centers. This function calculates the potential centers of circles that pass through 2 given points, P1 and P2, with the constraint that the circle's radius must be r. If the distance between the 2 points exceeds the diameter of the circle, no valid circle can exist, so we return an empty list. For valid cases, we calculate the midpoint between the 2 points and use geometry to determine the 2 possible circle centers. Additionally, if the 2 points are the same, the midpoint itself becomes the only valid circle center. Next, we define a third helper function, count_points_inside_circle, that counts how many points from the points list lie within a circle with a given center and radius. This function iterates through all points, checking if their distance from the circle center is less than or equal to the radius. Finally, we initialize max_points to 1 and start a nested loop to examine each pair of points in the list. For each pair, we'll calculate potential circle centers, which is where the next part of the code continues. Once we have the potential circle centers for a given pair of points, we iterate through each center and calculate how many points from the input list fall inside the circle defined by that center and the given radius. To do this, we use the count_points_inside_circle function. We then update the max_points variable if the count for the current circle exceeds the previously recorded maximum. This ensures that by the end of all iterations, max_points holds the highest number of darts that can fit inside any valid circle. Once all pairs of points have been evaluated, the function returns max_points as the final result. This approach ensures that we systematically check every potential circle that could enclose the maximum number of darts, leveraging efficient geometric calculations to make the solution computationally feasible. Here, we begin by importing necessary packages and defining the solution class. The main method, numberPoints, calculates the maximum number of points that can fit inside a circle with a given radius. We initialize maxPoints to 1, as a single point can always fit in a circle by itself. The nested loops compare every pair of points in the input array. For each pair, we calculate potential circle centers that can encompass both points using the find circle centers method. Then, for each center, we determine how many points lie within the circle using the count points inside circle method, updating max points as necessary. The distance method, defined here, computes the Euclidean distance between 2 points, which is crucial for determining whether a point lies within the circle and for finding the circle's center. To find potential circle centers, we start by calculating the distance between the 2 points. If this distance exceeds the diameter of the circle, we return an empty list since no circle of the given radius can enclose both points. Otherwise, we calculate the midpoint between the 2 points, which serves as the base for determining the centers. If the 2 points are identical, the midpoint itself becomes the circle's center. When the points are distinct, we use the Pythagorean theorem to calculate the perpendicular offset needed to find the 2 possible centers. This involves computing the height of the triangle formed by the midpoint and the circle radius. Using this information, we determine the offsets in both the x and y directions and calculate the 2 possible center coordinates, returning them as a list. Finally, the count points inside circle method determines how many points lie within the circle defined by a given center and radius. We iterate over all the points in the input, calculating the distance between each point and the circle's center. If the distance is less than or equal to the radius, we increment the count. To account for floating point precision issues, we add a small epsilon value when comparing distances. The distance method here is an overloaded version that calculates the Euclidean distance between a double array, representing the circle's center, and an integer array, representing a point. This ensures consistency in measuring distances throughout the program and completes our implementation. To solve this problem, we start by initializing max_points to 1, because any single point can always be enclosed in a circle. We also calculate n, the total number of points, which is 3 in this case. The outer loop begins with I equals 0, so we select the first point, p1 equals 1, 0. This point will serve as the reference for comparing against all other points to determine how many points can fit within a circle of the given radius. Next, the inner loop begins with j equals 1, where we compare p1 equals 1, 0 to p2 equals 2, 0. The distance between these 2 points is calculated as 1.0, which is less than or equal to twice the radius, allowing us to find potential circle centers. The midpoint between these points is 1.5, 0, and the vertical offset for the centers is determined using the formula for the height of an isosceles triangle, resulting in 2 potential centers, 1.5, 0.866, and 1.5, minus 0.866. For each center, we count how many points lie within the circle of radius 1. The first center encloses 2 points, and the same result is found for the second center. We update max_points to the maximum of its current value and the count from this iteration, which becomes 2. Now, the inner loop proceeds to j equals 2, where we compare p1 equals 1, 0 to p2 equals 3, 0. The distance between these points is calculated as 2.0, which is exactly equal to twice the radius. This means the offset for the circle centers is 0, resulting in only one potential center at 2, 0. We count the points that fall inside the circle with this center and find 2 points. Since this count does not exceed the current max_points value of 2, no update is made. When the outer loop moves to I equals 1, similar comparisons are performed, but no configuration yields a higher count. Therefore, the final output for this example is 2. In the second example, the points form a cluster, and the radius of the circle is 1.5. We initialize max_points to 1 and note that there are 4 points in total. Starting with p1 equals 0, 0 as the reference point, we calculate distances to all other points. For p2 equals 1, 1, the distance is square root 2, and we calculate 2 potential circle centers based on the midpoint and vertical offset. For each center, we count how many points lie inside the circle. This process is repeated for p2 equals 1, minus 1, and p2 equals 2, 0. By evaluating all potential centers, we determine the maximum count of points that can fit within the circle for this iteration. The outer loop then iterates over other reference points, p1 equals 1, 1, and p1 equals 1, minus 1, performing similar calculations to ensure we consider all possible circle configurations. After evaluating all points, we find that the maximum number of points that can fit within the circle is 3. In the third example, all points are close to the origin, so selecting the origin as the circle's center immediately encloses all 5 points. This makes the final count for this example 5. Summarizing the results, example 1 yields 2 points, example 2 yields 3 points, and example 3 yields 5 points. The time complexity of the solution arises from the nested operations within the algorithm. First, consider the outer loop where we select all possible pairs of points from the input list. For n points, the number of pairs is given by the combination formula n*(n1/2, which simplifies to O(n squared). Next, for each pair, we calculate the possible circle centers using the find_circle_centers function. This involves basic arithmetic operations like distance calculations and midpoints, each taking constant time, or O(1). Finally, for every circle center, we need to count how many points lie inside the circle. This requires iterating through all n points and computing the distance from the center to each point, which takes O(n) per center. Since there can be up to 2 centers for each pair, this step remains O(n) per pair. These steps together form the basis of our time complexity analysis. When we combine these steps, the total time complexity can be calculated. The outer loop contributes O(n squared, while for each pair, we perform O(1) operations to find the centers and O(n) operations to count points inside the circle. Multiplying these together gives us an overall time complexity of O(n squared, O(1) plus O(n), which simplifies to O(n cubed). Now looking at space complexity, the primary factor is the input storage for the points array, which requires O(n) space. Additionally, the find_circle_centers function returns a maximum of 2 coordinates per call, which contributes only O(1) space. Temporary variables used throughout the algorithm, such as those for intermediate calculations, also add a constant O(1). Since no additional data structures are used, the overall space complexity remains O(n). To put this into perspective, a brute force approach would involve enumerating all possible subsets of points to form circles, resulting in an exponential time complexity of O(2 to the power of n). The current solution optimizes this significantly by focusing on pairs of points and leveraging geometric properties, reducing the time complexity to a polynomial O(n cubed). In terms of best, average, and worst case analysis, the best case occurs when there are very few points, either 1 or 2, where the time complexity is O(1, because no pairs or circles need to be processed. In the average case, with a moderate number of points, the algorithm iterates over all pairs, leading to the expected O(n cubed complexity. The worst case involves a large set of distinct points, requiring a full traversal of all pairs and associated circle calculations, also resulting in O(n cubed). Mathematically, the Big O proof confirms this. The nested loop contributes O(n squared, and for each pair, counting points contributes O(n). Together, this results in the cubic growth O(n cubed, where constant factors are ignored in asymptotic analysis. One of the most common pitfalls when solving this problem is mishandling edge cases. For example, if there are fewer than 2 points or if all the points are collinear, many solutions break down, leading to runtime errors or incorrect results. It's crucial to account for these scenarios to ensure your solution is robust. Another frequent mistake is relying on floating point equality checks. Floating point arithmetic is not always precise, so directly comparing 2 values can yield unexpected results. Instead, it's better to use a small epsilon value, like 1 times 10 to the power of -6, to compare values approximately. Additionally, overcomplicating the brute force approach can be a problem, especially for beginners. The brute force solution should be simple and clear, as this makes it easier to debug and understand. Lastly, some candidates overlook the importance of optimizing their solution's time complexity. For instance, a brute force implementation with a time complexity of O(n cubed, or worse, might pass small test cases but fail for larger inputs. Always analyze the efficiency of your solution and look for ways to improve it when necessary. Another key area to watch out for is failing to pre-compute or memorize results. In an optimized approach, redundant calculations, such as repeatedly computing distances between the same pairs of points, can slow down your solution significantly. Using memoization or pre-computed data structures can eliminate these inefficiencies. Now, when it comes to interviews, it's vital to take a systematic approach. Start by fully understanding the problem's requirements, clarify constraints like the maximum number of points or the range of coordinates. Then, modularize your code by separating the logic for tasks like computing the circle, checking if points lie inside it, and iterating through pairs of points. This makes your solution easier to read, debug, and explain. As you present your work, discuss trade-offs between the brute force and optimized approaches. For example, does your optimized solution require additional memory, or is the math more complex? Finally, always test your solution with a variety of examples, including edge cases like overlapping points or minimal input sizes, as well as large datasets, to demonstrate its reliability and robustness. If you're looking to deepen your understanding, there are several related problems worth exploring. LeetCode 149, max points on a line, is another challenging problem that involves geometry and precision handling. LeetCode 587, erect the fence, focuses on computational geometry and convex hull algorithms. For a problem emphasizing symmetry, check out LeetCode 356, line reflection. And if you're just getting started with geometry problems, LeetCode 1232, check if it is a straight line, is a simpler one to practice on. Beyond the standard approach, there are also alternative methods to consider. An optimized geometric approach, for instance, leverages properties like perpendicular bisectors to reduce the search space. While this can speed up the solution, it does involve more complex mathematics. For very large datasets, a grid-based approximation might be useful. This method sacrifices some precision for speed by using a heuristic approach. Lastly, randomized algorithms, such as random sampling, can provide an estimate of the solution with high probability. These are faster for large inputs but come with the trade-off of producing non-deterministic results. Exploring these alternatives can give you additional tools to tackle similar problems effectively. That wraps up our walkthrough of the maximum number of darts inside of a circular dartboard. We explored the problem, reviewed approaches, and highlighted the key takeaways. I hope this session was valuable and inspires you to tackle similar geometry-based challenges. Don't forget to like, share, and subscribe for more insightful problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!